ყველას გამარჯობა ხალხო კიდევ ერთხელ. ერთი საკითხია, ანუ მე და შოთან ბევრი ვილაპარაკეთ რა ენაზე უნდა ყოფილიყო. ხო და ნუ გადავწყვეტეთ ბოლოს რომ იყოს ინგლისურად, ამიტომ არ გაგვიკვირდეთ, შეიძლება ყველა ჩვენთაგანს აქ ესმის ქართული, მაგრამ რაღაც რამდენიმე მიზეზის გამო გადავწყვეტეთ რომ იქნება ინგლისურად და მე მგონი რომ პრობლემა არ არის. ხო, სანამ უშუალოდ ამ თემაზე გადავალთ, პატარა შესავალს გავაკეთებ ზოგადად ამ სერიაზე. ანუ ხო, მოკლედ, so why we decided to do this meetup series, right? So we first of all, both of us, Shota and I, want this to be technical meetings or technical talks, as you wish. And the reason being is that we believe that this is the only format when someone can actually learn something new or something useful or something practical. Because I've attended a bunch of meetings here in Tbilisi or abroad where people usually talk about some projects, they just define a problem, what they wanted to solve, and then they just jump right away into the final results. And as personally, I don't really care about those results unless I belong to the same domain. Let's say if I'm attending a healthcare meeting and then a person just says that, okay, I had this problem and then I got these results, then I don't really care what kind of results he got if let's say I come from the finance domain, for example. We want to focus specifically what happens between the problem framing and the final results. That's the area or piece of this research that we are particularly interested in. And again, the reason is that, yeah, we believe that this is the case when you can actually learn something useful and practical, and when you get back home, you can actually implement something, whatever you heard here during the meeting. So that was our sort of motivation for both of us. Another point is that, so I'll start today, then the next meeting, we don't know exactly when it will be, so we will update you soon. So it will be still me or Shota, we don't know yet. But this does not mean that it's just for two of us like talking, right? So we want the opposite. We think that maybe all of you or some of you will volunteer and you want to decide to speak and share your experience or knowledge in data science or an ML field. So what I'm trying to say is that we encourage everyone to reach out and sort of express your interest in presenting your project or your problem if you think it's interesting and useful. So the only requirement that we have is that you have to be technical, right? It should not be like a general description of a problem or a project and then just results. So we don't want that. We don't want to like have that kind of talks in this series. Just to summarize, if you guys have a problem or a project you worked in the past and you think it's worth sharing with us with the local community, then yeah, please feel free to contact me or Shota, and then we can discuss and schedule a meeting for you. Another thing that I wanted to mention is that we also aim to talk about so-called hard problems. I don't know the better word, and I'll try to explain what I mean by hard problem. By hard problem, I mean a task or a question for which the answer is not known, for example, or it's not easy to find the answer in a textbook or even in research papers as well. And I'm saying this because I had that kind of experience when I worked at the previous small startup. So we were building the AutoML platform, and I had a bunch of such problems where, in which case, I could not, I wasn't able to find basically a known or a clear answer how to solve those problems, and so then, and I had to sort of think of a solution myself, which is, of course, a good thing in my opinion. And of course, I'm not saying that we will be discussing such problems on every meeting. Even today, yeah, I'm not going to talk about such problem. But I'm sure once in a while, if we just keep these meetings going, we will be discussing such so-called hard problems, or the problems for which solutions are not known. So just to give you an idea, just one example of such problem. So for example, you have a trained model, and you have access to the model maybe through the API or whatever, doesn't matter. And you can generate as many predictions or forecasts using that model. Then you also know what kind of algorithm was used to train that model. You have access to the training data. Basically, you know everything about this entire pipeline, but the only thing that you don't know is the loss function. Someone just trained that model and he shared everything except the loss function. So you don't know what kind of function they used to optimize. And the question is it actually possible to do the reverse engineering, and given all this data that I just mentioned, to guess or estimate the loss function? And so why is this an important question? For example, Facebook or Instagram, you know that they use a bunch of recommendation models to offer you some content, right? To populate your news feed every day. So they know what you're watching, what is your interest, and then based on that kind of input, they populate your news feed every day. But we don't know what kind of loss function they are optimizing when generating those recommendations. And I think it's very important, right? Because, for example, we know that depending on what kind of news you read every day, it can sort of somehow impact your opinion on some topic. And for some people, that impact is big, for some it's small, but knowing what kind of loss function they are optimizing, I think it's a pretty important question. So these are the problems that I mean when I say hard problem. And I think, yeah, if we keep going, I'm sure some of you have encountered similar problem in their own project. And yeah, we're happy to talk about these things and discuss it. Yeah, so, and one final sentence for this introduction. So as I said, our goal is to continue this series as long as possible. So both of us, Shota and I, are pretty motivated about it. And again, but of course we realize that if we want to have this in a long run, it's not sustainable if it's just two of us. So again, yeah, we encourage all of you to sort of volunteer or be interested in giving a talk and describing your project or a problem. And I'm sure if we do this on a regular basis, we will ultimately reach some nice results. So all of this, the networking or just a talk and answering the questions during the talk, I think should lead us to some nice results. And I believe it will be rewarding for all of us in general. Okay, that was the intro, and now I'll jump to the talk itself. So as you can see, and you see the title, yeah, there are two parts. So first will be about the benchmarks, and we will review a couple of algorithms for time series forecasting. and then the second part is the like best practices or common pitfalls that we usually make when dealing with time series projects. Title sounds rather general, and you know that when title of something is general, usually that work is ambitious. But unfortunately my presentation is not that ambitious, but I'm sure it will be useful for all of you. Doesn't matter whether you are, experienced or not. Okay, so since the first part is about the benchmarking the algorithms, so I will review the algorithms that I will be discussing first. So my goal is not to go into very much details in reviewing the algorithms. It's not the goal of this presentation, but shortly I will just go through them quickly. So we will be talking about these four. Maybe you guys already know about them and you've used in your practice, I don't know. But if there is someone who doesn't know about them, let's just review them quickly. So first one is so-called ARIMA, right? So AR, the first two letters in the name, stands for the autoregressive. So autoregressive means this equation that you already see. It means that the value of the variable, in this case y, can be forecasted by its own past values. So it's just a linear combination of its own past values. And in this case there are like p values, right? So epsilon is the error term. Then I, third letter in the name, stands for the integrated, and this means the differencing, right? So differencing is that operator, like first order. So there might be multiple orders of differencing in your needed for your specific sample. So first order is simply a difference between two neighboring values of y, and if you want to do the second order, you apply the same operator but already to y prime values, and you can proceed. And as you can read, it's done just to make your series stationary, because forecasting stationary series is much easier than the non-stationary one. And if you are interested in more details, there is this reference below the slide, so you can really check it out. It's a really nice book, and Hindman is like top expert in time series forecasting business, and he wrote this really nice book about the algorithms for time series. So MA stands for the moving average, and what it says is that the value of y that we want to forecast is a linear combination of the forecast errors. So epsilon usually denotes the error when you do the forecast. All of these three components that are combined into a single formula over there, right? So the first part, so the first part here is the autoregressive part, and the ones with epsilon is the moving average part. And yeah, again, it's a sum of two linear combinations, and we have y prime because we assume that we applied the first order differencing to the original values, right? And as I said, you can do multiple order differencing. It's up to you and up to the sample that you are trying to forecast. So therefore, ARIMA has three hyperparameters: P, D, and Q. So P denotes how many terms I want to include in the autoregressive part. D denotes degree of differencing, or how many times I want to apply a differencing operator to the original series. And the Q tells me how many error terms I should include in the equation. Um, so the next family of algorithms I will be talking about shortly is ETS. So as you can see, E stands for the error, T trend, and S means seasonality. And it's not, ETS is not a single algorithm. It's as it says here, it's a family of exponential smoothing models, right? And we will, let's review them quickly. So depending on what type of model you want to do, let's say error term can be additive or multiplicative. And this will become clear what it means. Trend can have like 3 different values or even 4. I don't have all of them here. And seasonality again can be additive or multiplicative or no seasonality at all. And let's say I want to consider a case when I have an additive error but no trend and no seasonality. In this case, this generates a very simple equation for forecasting. And so you see that, it's a weighted average, and the coefficients or weights for each point in time is alpha, then alpha times 1 minus alpha, and so on. So alpha is usually less than 1, and as you can see, it decays exponentially as we go into the past. That's why it's called exponential smoothing. And the equation below is basically the same equation, it's just a different way of rewriting it. That's it. So L is called a level in a time series literature, and we define it that way. So it's called smoothing equation. And this one is again another formulation of the same equation. So we need this because we will see it on the next slide, why we need these 3 different ways of writing same thing. So now let's consider a case when error is multiplicative and I don't have a trend and I don't have any seasonality in time series. So in this case, you have just L times the error, right? While in the previous slide, it was L plus the error, like over here. So that's the difference between being additive versus multiplicative. So that's all. And then again, another member of that ETS family is like additive error, additive trend, and multiplicative seasonality. And then these equations get complicated as you turn on all different components of the algorithm. Okay, so basically, I don't know, I think there are 20 or 25 different algorithms in this ETS framework. So therefore, model selection becomes a sort of problem or an issue in that sense, because you have 3 parameters, each of them have few different values, and there are multiple combinations that you should consider to choose the model, the right model. So, and because of that, then they came up with another algorithm. It's called complex exponential smoothing. So what is it, right? It's again very simple to formulate. So this formula is from the previous slide. So it's like a simple exponential smoothing. It's a weighted average of t minus 1 and y hat t minus 1. And in order to make it complex exponential smoothing, we replace every term in this equation by its complex alternative. So y hat is replaced by y hat plus e hat. And e hat is the error again, forecast error. And again, alpha is replaced with its complex alternative. Yt minus 1 is also replaced with its complex alternative, and same goes with every term in the equation. So what's good about this is that you have only 2 parameters to sort of tune, alpha 0 and alpha 1. And the error term also is into the play. It can directly affect the forecast. And Another thing is that having this complex part in the equation actually allows you to have oscillating weights instead of just exponentially decaying weights. That's the benefit of this algorithm. Okay, and the next one and the final one is the profit. I don't know if you've heard about it. It's the model that was created in Facebook and then open sourced by the Facebook, I think in 2017. At least the paper below says 2017, so probably it was open sourced in the same year. So why I want to talk about this? Because, and in the next section about the benchmarks, we will talk about profit a lot, because it's the most popular forecasting algorithm today. I mean, and it was downloaded, I don't know, tens of millions of times, I think, if I remember correctly. So it's by far the most popular one. Everyone is using it in industry, in academia. It's a very popular one. We will talk about it later. So now, what is it, right? So it's a sum of these three terms. So G stands for trend, S stands for seasonality, and H, holiday, is a holiday. So just to describe very quickly what it does. So it's based on this concept of change points. So change point, what is it, right? The change point is a point in time when the trend changes the slope. So if you look at that figure or a chart or plot, sorry. So these vertical dashed lines denote the change points in the time series. And once the algorithm identifies how many change points are there in the time series and the location of those change points, then you simply do the piecewise linear regression between them to build your trend, and then you are done. And in order to model the seasonality, then they use this simple formula, it's the Fourier term. And the number of the Fourier terms, this capital N, is your hyperparameter. You have to set it yourself in order to get the optimal model. So HT, as I said, it's a holiday, and what you do, let's say we are in Georgia and Easter is coming, then you just introduce like one hot encoded columns, and you just put one in a column next to an Easter date or some other holiday that we have here. So it's a dummy variable, that's all. So that's a very brief and rough description of the profit. So again, if you would like to know more, there is the paper, and it's described everywhere. It's because it's a very popular one. So I didn't go into detail because, as I said, our goal is not to review these algorithms in detail, and that's why I just did a very quick overview so that if someone is not familiar with it, they just understand what we are talking about. So now I'll jump to the benchmarks, which I think is the most interesting part. So the motivation for me to think about this was that at some point this year or in the past year, I don't remember, I realized that there are like a decent number of experts, time series experts, who actually dislike a profit a lot. And their main argument is that it's not an autoregressive model. As you saw, it's trend plus the seasonality. And we know that there are like a lot of data, a lot of processes in real life which is autoregressive, like stock price, for example, or exchange rates. I mean, there are some important processes which are autoregressive, and these people think that if an algorithm is not an autoregressive, it's useless. And then, then I thought, when I was researching this topic, I wanted to understand why they dislike profit. And then I read about these. So Zillow, you can read, so it's a US based real estate company. So they are busy with buying and selling homes in the US. And as it turns out, in 2021, they had a like a big problem. So they lost like $300 million in a very short period. And as you can read from that article, the reason they attribute that failure to the reason that they failed to generate good forecasts. And because of that, they lost that huge amount of money. So they fired a lot of people from the company because of that. And so you might ask, so what's the connection between Zillow and the Prophet? And as it turns out, the connection is this job listing from Zillow. So as you can see, they look for a senior person who is especially good at the Prophet. So when these people who criticize Prophet a lot saw this, so they just jumped into conclusions and they say that even today they repeat this argument, that the only reason they sort of lost that amount of money is because they use Prophet to generate the forecasts. Of course, then there were people saying that that's not true, that Zillow has very complicated neural network-based models or machine learning-based models, but nobody cared. As I said, even today, when people argue regarding the Prophet, they usually refer to the Zillow case to win the argument. And so when I read this, so I thought, okay, can I find some evidence in the literature that actually tells me that Prophet is that bad? So that was my next step. And surprisingly, it's very easy to find such cases in the literature, and I'll just show you a few of them. So the one on the left, so it's done by one of the experts in time series, and it shows that, yeah, Prophet is the worst algorithm here. Same goes here, it's the last place in the study for the sales forecasting. Same goes here, again, this one is for the sales forecasting as well. This one is for COVID-19, so Prophet is one of the last. Here it's for the USA inflation forecasting, so yellow bar is a Prophet, and together with the LSTM, they show that it's one of the worst algorithms. But the final sort of thing that I got really convinced that actually it might not be the best solution is this sentence that I read in Hindman's book. So Hindman, I already mentioned who is Hindman, right? He's a top expert in time series and the author of that book that I already showed you as a reference. So he says in his book, however, Prophet rarely gives better forecast accuracy than the alternative approaches. And then, if you are really interested in this topic, there is this Medium blog post by another expert. His name is Peter Cotton, where he actually discusses the Prophet in great detail, and he even tries to suggest some modifications you should apply to Prophet algorithm in order to make it better in general. And Sean Taylor, there is a tweet from Sean Taylor, and this is a guy who created the Prophet, and you can read what he said about, and when he said this post, he is referring to this one. And he says, I agree with most of it. And this guy, the Peter Cotton guy that I mentioned, the author of this blog post, is running a website called microprediction.com. And among many other things, he is also hosting a leaderboard on his webpage. And the leaderboard is for the Python packages for time series forecasting. So it's a huge leaderboard. I mean, I think he covers everything. It's amazing. So this is a screenshot from his webpage, and there is a Prophet, and the score he has, corresponding score is 1600, while first place has, 2100. So there's a big gap between top 3 and top 5 algorithms and the Prophet. Okay, so then what I asked myself was, okay, if Prophet is so bad, then what is the answer? I mean, what option do we have? I mean, which package that one should use? And in my opinion, answer to that question is Nixla. So this is just a screenshot of their webpage. Yeah, I just put this tweet from Sean Taylor, the guy who created Prophet, and actually you can sort of see how good is Nixla. I mean, it's not good because it's fast or because it produces better forecasts. I mean, the documentation that they provide is one of the best that I've seen, and I really like their ecosystem. So very briefly, I'll just describe what these mean. So this white block means that it says open source time series ecosystem. So what they have, they created a bunch of Python packages. So one is specifically for the statistical models, like the ARIMA, ETS, we've talked about. Then they have another library that contains machine learning algorithms for time series. Yet another library they provide is neural forecasts. They are these neural network-based algorithms for forecasting problem, and they have other stuff as well. So the why I like it, it's a very organized and very well documented. So it's easy to find answers to your questions when you start using their packages. And the one on the right side, the black one, it says TimeGPT. So TimeGPT is the name of the pre-trained model that they did actually, and Nixla was the first company who basically created a transformer-based model, and they were inspired by these large language models, right? GPT, and I don't know, there are a bunch of them already. So they thought that, okay, if transformer architecture works so well for the text, and text is a sequential in nature, so it should work also with time series because it's also sequential, right? And they created their own version of transformer architecture. They did not change the transformer, I think, but they just used the transformer as a building block for their neural network. And this is like TimeGPT is basically a first foundation model for the time series problems. And we will discuss that as well later. So I think what also we should talk about is the benchmarks that Nixla did. So yeah, it's called this slide Nixla versus Prophet. And again, so why? Just to answer the question, so why they want to benchmark against the Prophet? Because again, Prophet is the most popular package and widely used time forecasting package. And if you are a startup based in California, you want to beat Prophet. You don't have any other option. Of course, if you work in time series business. Just quickly what they show here. So this one is about the execution time. They are comparing themselves with Prophet's execution time. As you can see, the difference is huge. So yellow is Prophet and blue is ARIMA, but Nixla's implementation. And on the vertical axis, we have data sets. So M3, M4, M5, there is no M5 here, but I don't know if you're familiar with M3 and M4. M3, M4, and these names are associated with the competition, but specifically for the time series. So it's like a Kaggle, but only for time series problems. And the nice thing about these competitions is that usually those data sets are publicly available, and all the benchmarks that are publicly published most of the time are based on these M3, M4, M5 data sets, because they are not like a toy samples that someone generated with some Gaussian process or something like that. It's actual real life data. I think M5, the latest competition, it was based on a Walmart sales data, and it's a huge sample. So on the right, then there is a comparison in terms of the performance. So MAPE is the metric, or mean absolute percentage error. I hope all of you know what it means. And there are some cases here. You can see that profit is good, is better, but on average, yeah, ARIMA is doing a better job. Another comparison is for the neural profit. So basically, neural profit is a successor of profit, and the difference between them is that, as you saw, it uses this piecewise linear regression to generate a trend, but in neural profit, they use the neural network to learn the trend. So it's more sort of sophisticated in that sense. Again, same structure. This graph compares the execution time, and pay attention that we have a logarithmic scale here. And what does it mean? It means that the small difference on a log scale means a huge difference on the original scale. And they basically chose to do this comparison on a log scale because in the original scale, the blue bars are so small, they are not visible, right? So the difference in this case becomes even larger. But that makes sense, right? Because it's based on neural net, and neural net is much slower than linear regression. And again, this compares the accuracy, and we see the same story, right? It's Nixla is better than the profit. The next section is basically, once I've learned all about this that I just talked about, so obviously the next step is to sort of verify this on your own data. And so what the data that I have at my company, or not my company, but the company that I work at, is this monthly sales data. So imagine a company that owns a bunch of shopping malls in many countries, and you have the sales data from every store from each shopping mall. That's the data that I'm talking about. So you have like data from stores, from fashions or restaurants, entertainment. So it's a big variety of sort of domains that we get data from. And yeah, so it's a monthly sales data. It's a very simple. But the number of time series that I'm analyzing is like between 3,000, like 2,000 and 3,000 roughly. So it's a pretty decent size, I would say, to do the benchmark. So what I'm going to do, I'm going to just compare Nixla and profit based on this real life decently sized sample. So I'll start the comparison with the, I think, most interpretable metric and easy to understand. So it's called relative mean absolute error. So what we have here, so numerator is just a difference between the actual value and the forecasted value, y hat. And forecast, y hat here refers to either ARIMA, ETS, or CES. And in the denominator, we have mean absolute error of YT, which is an actual value, observed value, and Y base. And base here is a profit. So basically, if that ratio is smaller than 1, this means that numerator is better, and numerator is generated by ARIMA, ETS, or CES. And if that ratio or a metric is greater than 1, then the denominator is better, or the profit is better. So you see these distributions, and all of them are smaller than 1, on average, of course, and which means that all 3 of them are doing a better job than profit on this specific data. So next few slides are basically looking at the same point but from different point of view. So here I wanted to look at do the same comparison, but I wanted to look at different metrics, right? So RDM, so you have a definition for RDM above. I provided definition for RDM because it's not a common metric. I don't think you can see that in the literature, but we use it in our team for some reason, and I wanted to do the comparison based on RDM. So RDM basically stands for a relative deviation of means, as you can see from the formula. So what we see, again, we see that ARIMA, ETS, and CES, they are on average better than the profit. But CES is not that, it's closer to profit, but the clear difference is coming from ETS and ARIMA. So same goes with MAPE, or mean absolute percentage error, and same is true for scaled mean absolute error. So then also another interesting thing I think is to see in which time series the profit performs best, and that's what you see on the histograms. So and for different metrics, right? So for RDM, we can see that profit is best in 20% of cases, and for MAE it's like 10 or 12, and so on and so forth. So on average, profit is doing the best, the good job in like 13% or 14% of cases. And as a reminder, so I did this analysis on like roughly 2,500 time series. And the distributions below this box plot basically shows us what is the distribution when profit is the best model. And as you can see, when it is the best, it's doing a good job compared to other ones. And this is the last slide for this section. So I again just wanted to see how that metric was distributed across the buckets, right? So on the vertical axis, I have these buckets of the metric over here, and the diameter of the circle here denotes the number of time series ended up in that bucket. The number is not provided here, but it's just to give you an idea, how the metric is distributed for each of those algorithms. And basically the picture is the same. So profit is shifted downwards, and all these 3 are shifted upwards. And there is no observation in this bucket for profit, while the best bucket, we at least some time series ended up in the best bucket for the other 3. And basically, for other metrics, same story, right? So profit is on average doing a worse job than the Nixla implementation of these statistical algorithms. So just to summarize, I haven't mentioned the execution time. And that's also, I think, the biggest point here. So as you saw from the benchmarks that Nixla did, so in terms of execution time, Nixla is like a clear winner, and I observed the same, obviously. So just to give you an idea, so I have to build like thousands of models in this project, and Profit like has a bunch of hyperparameters, and I usually try to tune them in order to optimize the model. And to do this for that number of time series, it took like 2 days on my local machine. Almost 2 days, roughly. But when I did Nixla, exactly same amount of time series, same procedure, it was done like in 20 minutes or 30 minutes. So the whole idea is that depending on, well, if you have, let's say, 1 or 2 time series, then you can use Prophet and at least try Prophet. But still, it makes sense to try simpler traditional statistical algorithms. But if you want to scale it up, then a Prophet, I don't think anyone should use Prophet because, as I said, yeah, it's very expensive in that sense. And if you want to, yeah, again, have thousands or tens of thousands of time series, yeah, Prophet, I think, is not an option here. Yeah, for example, this M5 competition that I mentioned, it contained 100,000 time series, and you can imagine what will happen if you use Prophet to win that competition. Okay, so this is the was end of the benchmarking part, and I've mentioned these foundation models. I just wanted to spend few minutes on this topic because it's a really new one. It started, as I said, this time GPT by Nixla was released by the end of the last year. So it's a very new thing. And idea is, so I just repeat one more time. So why you want to have this pre-trained large model, right? The reason is that if you have such pre-trained model for time series, then you can do so-called zero-shot inference. And what it means that you can just take your pre-trained model, for example, time GPT, and you can just, you have your time series, you just pass it to time GPT and it will generate forecasts without training. That's what zero-shot inference means. And obviously that's a very neat and very useful. And at some point when we reach to a point when these foundation models actually perform really well and are reliable, probably all of us are going to use them like we do for language models now. Here's just a list of these foundation models. You can see there are, I don't know, 6 or 5 already released since December last year. And I've included the papers. If you're interested, I think, yeah, we can share this presentation later, and you can access those links if you really want to understand how those models are trained. So some of them are from in the industry. So last one, for example, is from Amazon. This Moirai is from Salesforce. Basically, every company that has money and experts, all of them are trying to train these GPT type models, but for time series, because it's an important important problem for all of us, right? Time series are everywhere. Then, just for fun, I've included again some benchmarks, but for these foundation models. So this GPT, this is one for time GPT. So this last row is time GPT. So bold numbers in bold means the top performance. Numbers that are underscored a second place. Numbers that have this dotted line third place. So you can see that time GPT is always in the top 3. But this is not an independent benchmark, by the way. This is done by the same company, or Nixla, that released time GPT. So we would like to see the independent one. So this is another benchmark for the LagLlama. LagLlama is another foundation model. And I've highlighted some sense so that you don't have to look at these numbers. I try to highlight what it means, what they want to say. They say that simple, seasonal, naive can outperform LagLlama, which is actually very surprising. They also benchmarked, the Nixla benchmarked the Amazon's model as well, and again they find that simple statistical ensemble based on ARIMA, ETS, and CES are actually better than this expensive model released by Amazon. Same goes with Salesforce. They beat it with using simple ensemble, but this one actually is published by the Amazon team. So they actually are really competing with each other. It's like a race because they want to prove that we are the ones who have really the best model in this domain, because obviously they spend millions of dollars to train these models, because the data set itself is huge. I don't know, billions of points they are training their algorithms on, and it's expensive, and obviously they want to be the best, of course. And based on this table, you can see that Kronos can beat the statistical ensemble that they showed, that you saw on the previous slide. So we don't really know, basically. The long story short, it's a really new field, and we don't really know today, what will happen. But I don't know, I think by the end of this year, we are going to have more clear understanding whether these foundation models for time series are actually useful or not, and if they are, who should we trust? Is it Nixla or Amazon or someone else? We don't know. So I've included these two links as well, just to, this link is a GitHub repo, the first one, and you can find a bunch of evidence there why transformer-based architectures are useless for time series. But the next one, as the title says, it says completely opposite, that transformers are good for time series. So there is a lot of ambiguity about that topic, and I just wanted to share it with you. So now this is my second part and the final part of this talk. So as I said in the introduction, so we will talk about what kind of mistakes usually data scientists do when they deal with time series. And that's completely normal. I'm not saying that I'm not making mistakes, I also do. And the reason I think is that time series is a very specific domain. And I'm sure most of us here in this room, we come from a different background. We are not statisticians, we are not economists, so we were not trained at the university to do the time series. And therefore we lack like a systematic knowledge that is required to do time series problems properly. That's why I think it's useful to talk a couple of points that I find is useful, and we usually make mistakes in those specific areas. So first one is that you should always benchmark, and I think most of the part of this talk was about benchmarking. I hope you are convinced by now that you should always try to benchmark your algorithms or your models. And one very famous example of that is that you find a lot of papers published, I think, daily, or if not daily, weekly. So a bunch of them, when people try to really design these very fancy deep learning algorithms to forecast, let's say, stock price. And everyone wants to be able to forecast the stock price, right? Because it's the most rewarding problem to solve if you can solve it. But we know that stock price and some other similar processes, they represent random walk. So what is a random walk? Is a process when future value of a variable is current value plus a random noise. That's a random walk. And we know that the stock prices, for example, follow that process. And you'll find a bunch of papers where, like authors try to design really clever. I'm not saying that they are not clever. They are very smart people, and they come up with very fancy architectures for neural nets to do the forecast and guess the stock price, but they are lacking that benchmark basically. And as it says over there, naive forecast is theoretically the best model for a random walk. So naive forecast is a forecast what it is. So your last observed value is your forecast. It's like simplest model that you can come up with. And for random walk, one can prove that naive forecast is the best one. And you'll find the papers when they don't do the benchmark against naive forecast, even though they try to model the random walk. And this is just one example. It's a random walk process, and if we zoom in on the forecast horizon, you see that the red line is a naive, and the green line is a neural network, and you see that there is no significant difference between these two forecasts. So one thing I already mentioned on a slide, but I mean, you should always try to choose the right benchmark and as simple as possible benchmark for your problem, just to make sure that you are doing something reasonable. And another thing that you might encounter in the papers is that when they come up with a new algorithm, they usually test it on like 5 or 10 data sets or time series, and that's also not a good idea. And another one is, this is classic, like avoid data leakage, right? All of us know what does it mean. And basically it means that if you want to process your data, you have to split your data first and then apply your processing, and not the other way around. But the second point, this wrong forecast horizon, this is really subtle, and many make mistake there. So what does it mean? Let's say you want to train a model that forecasts 1 day ahead. And during the model development period, you created a variable like daily average of something like temperature, and you included your average temperature as one of your independent variables. Everything's fine so far. Then you deployed your model in the production, and someone who is supposed to use the model, so they will make a forecast at 1 p.m. for example, or 2 p.m. I don't know, because that's when people are at work, right? But at 2 p.m. when you generate your forecast, the day is not over yet. So, but one of your variables is average temperature, daily average. So what you'll do, you'll compute this average based on the data that you have up to 2 p.m. Let's say if you want to make forecast at 2 p.m. And it will generate something, no problem. But the problem is that during the training phase, we've used daily average. So we use the entire day to compute our feature as an independent variable. So which means that during the forecasting period, I'm using the data up to 2 p.m. to compute the variable, but in the training period, I've used the entire day to compute the variable. And this means that there is a data leakage because I've used future observations to compute my variable in the training period. And the third one I wanted to mention is that there are cases when you want to use one time series to forecast another one. And there are very frequently these two time series don't have same length. So for example, the first one, the independent one, might be like 6 months long or a year long, let's say 12 months observations, and the second one that I want to forecast contains like 6 months data. So they don't have same length, they do not start on the same day, they do not end on the same day. And if we are not careful, then same problem can happen, that some future points can end up in a training phase. So therefore, we want to make sure that these two time series, or whatever number of time series we are considering, they are aligned in time. to avoid that leakage. So again, this is also very famous, popular topic, data partitioning. So we all know, I assume that in case of time series, we cannot do the standard k-fold cross-validation, because usually, traditionally, k-fold cross-validation means that you randomly shuffle your sample and then you make a split. But we can't do it in time series because we have a time dimension there, and data is not IID and it's not exchangeable. So therefore, it's not a good idea to randomly shuffle your time series and then split it. So, by the way, when I say time series, I don't necessarily mean that kind of data. It's just here we have just a single variable. When we say time series, we mean any sample that has a time dimension in it. So any 2D table that you might have, and if you know that there's a time in your table, time dimension, time column, whatever, it is already a time series problem. So it doesn't have to be this, just a single curve. So therefore, that might confuse some people, right? So when they see this 2D table, something that it's like it's not a time series because it's just not a single curve, and they might apply this random shuffling and splitting. But yeah, anyway, so any sample that has a time dimension in it is a time series problem. So very quickly, to do the times cross-validation for time series, let's distinguish two things. So fixed origin or rolling origin. So fixed origin means you pick a specific time point, let's say January 1st, 2024, and everything before that time point is my training sample, and everything after that time point could be my test sample. But there could be a rolling origin, and rolling origin, as the name suggests, means that, let's say I choose the January 1st as a first splitting point, then the second splitting point would be, I don't know, February 1st, and third one would be March 1st. So basically this splitting point moves forward across the time axis. That's the rolling origin. And as you can see, there are multiple options for the rolling origin scenario. So first one is expanding window. This means that when the origin moves into the future, the training sample gets larger and larger, right? Because if I started on January 1st and now I move to the February 1st, the entire January is already become the part of my training sample. So that's why it's called expanding. And test sample, size of the test sample is usually fixed in every scenario. But in a rolling window, what happens is that you fix your training size, you fix your test size, and you just slide across these windows across the time axis. So the size of the training partition is constant in a rolling window case. And then the one below, you can start with expanding window and switch to the rolling window, or you can do the combination of both, depending on your use case, I guess, and the size of the time series that you've got. So second point is, standard k-fold CV, and I was really surprised when I found out actually that you can use traditional random shuffling in a case of time series. I didn't know about this. And I've just listed but there are lots of conditions to be met to be able to use that standard k-fold for time series. So it has to be stationary series, and there should be no correlation between the different folds, and model that you are using should be able to deal with the missing values. So there are a bunch of conditions. So if you're interested in this, here is the paper, and you can take a look at it to understand how that can be derived. But just so you know, you can apply standard CV for time series as well if these conditions are met. And the last piece is, just how should we do the data partitioning. So if we have short time series, and I can make it stationary somehow, then you can use standard cross-validation for that scenario. But in other cases, then we should stick with the time series CV. And again, if I have long and a lot of data, then rolling window is nice. If it's short, then we want to start with expanding, because if you have a short time series or small number of data points, you don't want to lose your points initially when you start your training. So it's better to employ the expanding window so that you can accumulate all the future points in your training sample. And then you can switch to the rolling window. It's up to you if you want to do that. This one is about the metric. So if you're familiar with the time series literature and you remember that from the university or from your practice, there are a bunch of metrics in forecasting literature, a lot of them. And one can summarize them, I think, based on this table. At least this table helps me. There are 3 dimensions in the metrics usually, time series metrics: error, scaling, and aggregation. So error is just a difference between actual value and the forecast, but there we have to decide, do we want to take the square or just an absolute value? So we have 2 values in this dimension. And then we usually do the scaling. So why do we do the scaling? Because most of the time we have a lot of time series in a data sample, and they have different scales. So one could range from, I don't know, 10 to 100, and another could range from 10,000 to 100,000. So in order to be able to compare these time series on different scales, we need to do the scaling to the metric. And these are the bunch of different types of scaling you can apply. So per data set, per series. So what does it mean, right? If you want to scale, you have to calculate the scaling factor based on your sample. And the question is, on which level should I compute that scaling factor? Is it based on entire data set, entire series, per step, or relative? So relative is, for example, MAPE is a relative metric because it's a ratio of the errors. And there is in sample, out of sample. What does this mean? Usually when they scale the metric, they want to use the Bayes forecaster, like I did in the case of profit. So profit in my calculation was the Bayes forecaster. And they usually use these Bayes forecaster's errors to scale their original metric. And then you have to decide what kind of errors you want to use, in sample or out of sample, depends on your time series. And finally, all of this is aggregated because we do this comparison for multiple points in time, right? We are not comparing just one forecast. We usually do forecasts in, let's say, for the next 7 days or next 12 months. So in order to get a single number, I have to aggregate all these 12 numbers if I do monthly forecast, for example. So either do mean, median, or geometric mean. So combination of these 3 dimensions, different combinations, usually creates this bunch of time series metrics. So I'll just go through these very quickly. So what it says, I'm going to read them, just read them. So use same error type for optimization and evaluation. So why? Because we know that square is related to optimizes the mean, while absolute value optimizes the median, right? We know this from machine learning textbooks. And some people say that, yeah, using, let's say, squared error for the optimization during the training, and then using mean absolute error when we evaluate the models doesn't make sense, because I used algorithm that optimizes the mean and not the median. That's the point of this first sentence. And the second one, yes, is just very simple. Use scale-dependent metrics only for time series with the same scale. I already talked about this. Then evaluating your models using multiple metrics is a good practice, because that sort of you can convince yourself that whatever model I trained is actually best one on multiple different levels. So that's why in the papers where they discuss forecasts, usually there are a bunch of metrics that they compute for every model, and that's a practice. Though when data set is large, usually all these metrics agree with each other, and that also makes sense. And the last one, I guess, yeah, R squared. R squared is, yeah, it's a very popular, widely spread metric everywhere in papers, in textbooks. But yeah, it's a dangerous one, because the purpose of R squared is slightly different than evaluating the forecast, and the reason is already there. And MAPE is also a very popular metric, and yeah, it's not a good idea to use it for the small values, because MAPE involves the ratio, and when you divide on a very small number, it just blows up and doesn't make sense. And okay, so here are a couple of special cases. So when we have like seasonal data, it's not a good idea to use the percentage errors, right? Because when there's a seasonality, you have a big peak, for example, or a dip, and either you divide by big number or by small number, and again, that's not a good idea. So it's better to use scaled, or use per series or global scaling for seasonal data. And for series with trends or structural breaks, right? What is structural break? Structural break is like something that happened during COVID-19, when there was some process and all of a sudden everything died. So that's a structural break. Some kind of shock that happens to the process, the data generating process. In that case, it's again, using scale-free metric may not be reasonable, because you have to compute the scaling factor, and everything depends which time points you use to compute that scaling factor, right? And it might not be relevant. Let's say if there was a COVID-19 and I compute the scaling factor, which contains, based on data points that contains the COVID-19, then that scaling factor cannot be relevant for other time points, right? So that's why it's a good idea to use per step scaling rather than scaling that is per series or per sample, so on and so forth. The third one I already mentioned on the first slide, I think. So you have to decide you want to use in-sample or out-of-sample errors from your base forecaster. Let's say if test sample is really different from the training sample, then of course the errors for the test sample are really different from the errors from training sample, and you really need to decide which error you want to use as a scaling factor for your metric. And the last one is use per series scaling only for scenarios with no trend. So why? Because when you have a trend, and especially if you have a strong trend and it increasing or decreasing rapidly, and you compute your scaling factor based on your entire series,
it is not that useful because you are applying that same scaling factor to every point in your time series, and your point in the beginning is very small than the point that you have by the end of the time series. So scaling all of them with the same factor is not a good idea. And yeah, so there's outliers. I think that's very trivial for all of you. Yeah, we know that using average for outliers is not a good idea, so use median or use absolute errors instead of squared errors just to avoid this impact from the outliers. So this is a diagram that I found recently, and I think it's really useful. So it just asks you, I don't know if I think it's not that visible, but what it does, it just starts with a question about your time series, and based on your answers, it will recommend what kind of metric you have to use. So I think it's really neat. So next point is, judging your forecast based on the plots, and I've seen a lot of people doing this, and that's not a good idea. And just here's an example. So we have multiple models over here trained. So ETS is the blue one, naive fixed origin is the green one, and naive rolling origin is the red one. So if you look at this, you see that blue is not that good because we have, this big difference between the actual is the black one. So we conclude that the red line is the best one here. But if you look at this table, you actually see that ETS is the best one, and ETS is the blue line, right? So why? So basically this I is deceiving us, right? So, and the reason is that we look at this small horizontal displacement between black and red, and that makes us think that the red is the best one. But what we really need to look at is the vertical displacement. And that's the reason why we usually say that, okay, red must be the best one, but that's not the case. So same here. So this is again a random walk and very stupid forecast, right? Just straight lines. And you might think, okay, if you look at this horizontal line over there, this can't be true, forecast can't be so trivial, right? So I'd rather choose maybe this one, yellow or purple, because it at least has some trend. But again, as I said, naive is the best model here, and you can see from the table. So long story short, we should always judge based on the metrics and not based on the plots. And this is my last slide. So when we do the benchmarks, we really want to know whether the difference that we see actually makes sense, or it's just a coincidence and that happens because I have this specific realization of this sample. So usually you do the statistical test to make sure that your results actually are credible. So this, simple diagram, whether you want to compare two models, yes, go there. You have a normality assumption for your data. If yes, do this test. If not, do Wilcoxon. And if you want to compare more than two models, and again ask normality assumption, let's say your errors, your errors do follow normal distribution. If they follow, you can do the famous F test, and if not, you can do a Friedman test. So I have this asterisk here, and the only reason I have it is that these tests, Mariano and Wilcoxon, they are designed to compare two forecasts only at a specific time point, just two numbers. And in practice, we usually want to do multiple comparisons, right? Because we generate multiple forecasts. And you know that if you repeat your statistical significance test multiple times, you have to do that correction. Bonferroni, there are others, but Bonferroni is the most famous, I guess. So you need to apply that correction if you want to compare multiple forecasts for two different models. Yeah, that's all. That's all I wanted to cover. So if you have any questions, I'm happy to answer. And again, thank you everyone for coming. Andro. Tu არის შეკითხვა? კი.
Yeah, I wanted to ask you about time series in supervised setting. How did we do benchmarking?
How to do benchmarking for
where it stands this benchmarking? Is there any results? It performs better than the statistical ones?
Oh, you mean if ML algorithms perform?
Yeah, if you use classical tree-based time
Yeah, so
setting.
Yeah, that's a good question. So I haven't done that comparison for that same data set, and actually that's probably the next step for me, because yeah, it's not like my personal project or something, so it's related to my work as well, and I'm going to do that. That part, and actually that Nixla released another package or algorithm that is basically tries to do the so-called hierarchical time series. So hierarchical time series is a special case when, let's say I was talking about the shopping malls, right? So shopping malls, you have a bunch of stores in every mall, and today what I do, I forecast every single store separately. And obviously what I can do, I can also forecast the entire mall. So aggregate the sales, monthly sales, I can sum it up on a mall level and do the model on a mall level as well. But I'm sure that if I sum up my forecasts on a store level, they would not agree with the forecast that mall level model is going to generate. And that's where this hierarchical forecasting comes in. So these two things, like using ML algorithms for time series, that I would like to do, and that part as well, this hierarchical stuff, I think it's a very interesting, because I've never used it in practice, and I really want to do that as well. Yeah.
Thank you very much for the lecture. I have a few questions.
Go ahead.
So first of all, I want to ask about data preparation. You said that we should split data set first, and I'm curious, should we take difference before splitting or after splitting?
Yeah, I think you should do it after splitting.
After.
Yeah.
If we have for train and test different result about stationarity, what should I do in this case?
Sorry, different result about what?
Stationarity.
Stationarity. Yeah, that's a big problem, right? I mean, when the test sample doesn't behave in the same way as a training sample, that's usually what happens. I don't think, personally, yeah, any manipulation you do to make your test sample resembling your training sample, that's not a good idea. I don't think we should do it. I think we just simply have to embrace that your test sample is going to be different, because otherwise, I don't know, if I try to make, apply. So one thing you can do is come up with some stationarity transformations to make your training sample stationary. And you're lucky if the same transformation is going to make your test sample also stationary, but probably that won't happen. So that's usually the problem, right? In a production, you are not going to get the same accuracy as you got during the training phase. So the estimating accuracy in a production is yet another and very interesting research field, in my opinion, because There are some methods where when you don't know, you don't have, like you can observe your independent variables, but you don't obviously observe the dependent variable. But there are some algorithms that actually tries to estimate what is the to what extent your production sample shifts from your training sample, and based on that, they try to make the correction and do some reweighting of the forecast in order to compensate that data distribution shift between test production sample and the training sample. Yeah.
Okay, thank you. Next question is about stationarity. As I understand, we have two types of stationarity, weak and strong. And what kind of test or statistic test we should do for understand how strongest our stationarity? Because as I understand, at 4 it's common metric, and we have diversity of tests for doing something specific.
One that just comes to my mind. So I would not sort of divide stationarity as weak and strong. It's not binary, right? It can be the magnitude of stationarity. I mean, could be depending on your trend, right? How strong is your trend or seasonality? Yeah, I would not divide it into just two classes, like a weak and strong. And the one test that just comes to my mind is this Dickey-Fuller test that actually can tell you, for example, whether your time series comes from if it has a unit root or a random walk. That just comes to my mind right now. But maybe there are others as well. I just can't think of.
Okay, thank you. And last question, okay. So we have an example about monthly data set, yes, about, and Prophet, as I understand, will show us more better result. My question not about this area, a question about seasonality I wanted to ask. How do you handle multi-seasonality in Sarima model? For example, we have data set with hourly, daily, and monthly seasonality.
Yeah. So in my case, there was just monthly.
Yeah.
If it was the seasonality, it was just monthly. So there is no hour, no week, only monthly case. So so for example, in Prophet, if you want to use Prophet, then it has a specific component that is responsible for the seasonality, these Fourier terms, and only thing you can do there is to just choose how many Fourier terms you want to sort of use to model your seasonality. That's one option. But for in case of ARIMA, so in my case, I don't know if you paid attention, but it was like auto ARIMA that I used from Nixla's package. So the way they so the ARIMA, so it's not SARIMA, just to be precise. So it out of the box, it doesn't care about the seasonality, right? It only has these components, moving average and autoregressive, and that's it. So that's what I use. So I haven't used Sarima, so I don't really know how well Sarima can handle the seasonality part of the time series. But one thing, just to mention, as I said, we do like thousands of time series at one time, like at the same time. So it's really hard for us to examine exactly what goes on within every time series. So we do this on scale, and we don't have time, to be honest, to go in detail and analyze, let's say, what went wrong for a given store, for example. The biggest ones we might analyze, the big stores, like generating the biggest incomes, but we can't afford, to be honest, to really analyze every time series and just check whether how well the seasonality was captured or not. That would be nice, but we can't afford that because of the limited time. So that's why, I mean, this is a good question, just to emphasize. So doing something like analyzing 2, 3, or 4 time series is completely different story compared to when you have to analyze hundreds of thousands of time series. 2 different approaches, and that Nixla really shines when you want to scale up your calculations, because it's very, very fast. And in addition to that, it also offers this automated algorithm. So they try to sort of automate the whole tuning process for you to make it even faster. So that's the point here. Yeah. Thanks. Are we done?
You mentioned you had varied from 2,000 to 3,000 time series, right? And the M5 has like 100,000 time series.
Yeah,
right?
yeah, I think so. Yeah.
So when I imagine like typical article, it's just looks at 1 time series, right? So even if you have thousands, there is nothing for 1 time series to gain from another time series.
Yeah.
But, well, if you introduce some exogenous variables based on other time series, like aggregations,
Mm-hmm.
by
Yeah.
the definition, you can get some, you can create some input from one time series to another.
Yes.
But is there any other way not to like handpick this aggregation, or maybe not spend as much time on feature engineering for time series, such that, or some algorithm that would determine like from which time series it should get
Mm.
from?
Yeah, I don't know, to be honest. I don't have answer to that question. The one thing that comes to my mind is this VAR, but yeah, that actually tries to catch a correlation between different time series. But if there is any specific approach that helps you in identifying a time series that would be sort of helpful for your given time series of interest, I don't know, to be honest. No. Any other questions? Okay. Yeah, thank you everyone.